Okay, today we're talking about the trigonometric form of a complex number. The goals, we want to plot a complex number in the complex plane, whatever that means. We also want to convert between standard form and trig form, and to multiply and divide complex numbers in trig form. So let me start with something you may not know how to do. We want to graph z equals negative 2 plus 3i in the complex plane. Well, here's the idea. You can think of z as an ordered pair. The only important information in this statement is the negative 2 and the 3. In other words, having the real part and the imaginary part. So there's no reason why you couldn't express z as an ordered pair, negative 2, comma, 3. So we know by the order which part's the real part, which part's the imaginary part. And then we'll graph it not in the xy plane, but in the complex plane, where the horizontal axis, the axis you normally think of as x, well, that's going to be the real axis. So think of a real number line. The vertical axis, the one you normally think of as y, we're going to call that the imaginary axis. And then plotting, it's as simple as it was to plot back in beginning algebra. So we're going to go left 2 and up 3. 1, 2 to the left, up 1, 2, 3, and plot a point. That's it. That's z. Well, you thought it was going to be harder than that, didn't you? But that's it. Now, okay, this leads me to something, the idea of the absolute value of a complex number. Okay, so what is like the absolute value of, say, negative 5? Yeah, if you take the absolute value of negative 5, you get 5. If you take the absolute value of positive 6, what do you get? 6. What is absolute value measuring? Distance from 0 on a number line, for instance. Well, we can extend that definition to the complex plane. For any complex number, we can define the absolute value of that complex number z to be the distance from the origin. So we could draw in a line here. It's not, this isn't, z is a type of vector, but we don't draw an arrow to go with it. So this line that I've drawn, we would just want to find the length of that line, which is the absolute value of z. But z is just the thing, just the dot in red. As a graph, z is just the dot in red. As we've done so many times before, we're going to drop a perpendicular, and then what have we created? A right triangle. What formula can we use to find essentially what is the hypotenuse of that right triangle? The good old Pythagorean theorem. What is the directed length of the horizontal side? Negative 2. What's the length, actually, of the vertical side? 3. So how could we find what we're about to define as the absolute value of z? Well, we're going to take the square root of something squared plus something else squared. Whoops. So fill it in for me. What do we get? Negative 2 there and 3 there. Let me go ahead and switch back to green here. So we get that the absolute value of z is, well, square root of 4 plus 9, so root 13. Does everybody agree with that? So that, and again, we use absolute value bars just like before. That would represent just the distance from the origin 0, 0 now in 2 dimensions that z is. So we've generalized the definition of absolute value from a one-dimensional number line to a two-dimensional plane, essentially is what we've done. Does that make sense to you? So what's the more general definition? The definition of the absolute value of z. Okay, if z is equal to a plus bi, where a and b are real numbers, then the absolute value of z, which we often call r, is the square root of a squared plus b squared. It's the Pythagorean theorem. Make that connection. It's also the same formula we used for the magnitude of a vector, isn't it? Make those connections. They're both the Pythagorean theorem in different contexts, right? Make those connections and there's less to memorize. Okay. There's also something we want to talk about, an angle we want to talk about back in this picture. And it's the same as the direction angle of a vector. We'd like to talk about this angle here and how we could get it. So how could we get that angle if we generalize to B and A? What trig function is going to involve that angle? And it's the same formula as the angle that we got in for vectors in the last section. Tangent of theta equals B over A. Same exact formula. So this is the definition of the absolute value. But let's talk about theta. It's a direction angle for z, for A plus BI. So the tangent of theta will be B over A. So we've got two special formulas here. And you need to know them for vectors, and if you know them for vectors, you know them for complex numbers, because again, a complex number is a type of vector. We don't draw it using an arrow, but it is a type of vector. Okay, now, any questions? So now we can talk about the trig form of a complex number. So let me draw that picture once again. I don't have to draw it in the first quadrant, but let's suppose for the sake of argument that z is in the first quadrant. And so we create that right triangle once again based on the position of z. We say that it has sides that can be directed lengths. In the first quadrant, they would both be lengths. But let's say it has legs of directed lengths A and B. Then what do we know? We know that this guy is the square root of A squared plus B squared. But I don't want to call it that. I want to call it by its other name that I gave it just a little bit ago, R. We often let R stand for the hypotenuse of a triangle, right? We've done that before in here. So I want to talk about a new form, the trig form of a complex number, z equals A plus BI. And I'm just going to state it, and then we'll talk about where it comes from. So z equals A plus BI, this is the standard form. We call this standard form. Standard form. But the trig form works in many instances a lot better than standard form. The trig form looks like this. We can take R, the absolute value of z essentially, that's what R is, and multiply it times the cosine of theta plus I sine of theta. And this is what's known as the trig form of a complex number. Now I want to convince you of this. So let me go ahead and distribute out that R. What do you get if you distribute out this R? So this is the formula I want to focus on. That's the trig form. Let's be clear about that. That's trig form of a complex number. But what is this equal to if you distribute out the R? R cosine theta plus Ri sine theta, yeah. Let's make it I times R sine theta. Same thing. Multiplication commutes it. Doesn't matter what order you do it in. Would you agree that that's what we get? Okay. Well, look. All we're saying then is this A right here is R times the cosine of theta. We already knew that from SOHCAHTOA, right? The ka part of SOHCAHTOA, you can get that. That's saying that A, the adjacent side to this angle theta, is the hypotenuse times the cosine of theta. We use this formula to find the horizontal component of a vector as well, remember? And then what is R sine theta? That's B, isn't it? From the SO part of SOHCAHTOA, we know that we can take the hypotenuse and multiply it times the sine of theta, and that will give us the opposite side, won't it? And again, that's the formula we used back in the last section to find the vertical component this time of a vector. So make that connection. These are the same formulas over and over again, okay, that we use in this class. So this is the way we usually write it, though. We factor out that r. And in fact, there's a nicer, cleaner form. It's really just a shorthand. We say r cis theta, which stands for this thing up here. So r cis theta is a shorthand way of writing r times the whole thing, cosine theta plus I sine theta. It's just a nice way to write it. Okay, so that's trig form. So I'll show you what it's good for in a little bit, but let's practice converting to trig form. So here we go. Convert to trig form. Part A, z equals the square root of 3 minus I. Just for fun, let's graph this thing. Okay, it's not that fun, but let's graph it anyway. So what would the first coordinate on the graph be? The real part would be radical 3, which is, I don't know, 1 point something, it's 1.8, 1.7 something. So, just estimate over here somewhere, right? And then negative I minus I, what would the corresponding coordinate be? Minus 1, right? So somewhere over here. So which quadrant? The fourth quadrant, yeah. Okay. So why do I mention that? Well, it's helpful to make sure that you're in the right quadrant angle-wise when you find theta. So it's helpful to, at least in your mind, picture what the graph should look like. But to actually find the trig form, you don't need this graph. So let's go ahead and do it. Trig form, remember, the easiest way to remember it is z equals r cis theta. If you can remember this short statement tells you exactly what you need. You need r, which is really what? The absolute value of z, yeah, which is the hypotenuse of the triangle that you could draw in here. And then theta, we know what theta is. It's the direction angle, right? Okay. But the direction angle is not actually unique, is it? So as you might find out very, very quickly, there's more than one representation of the complex number in trig form, because you could just add or subtract multiples of 360 or 2 pi if you're in radians to get another representation from the angle, from theta, that is. But we'll usually take the one between 0 and 360, or it might be easier to take the negative angle, but one of those two. Okay, so this tells you what to do then. I need r. So r is equal to, okay, square root of something squared plus something else squared. What would these somethings be? Oh, let me go back up. What would those somethings be? So root 3a, remember a squared plus b squared, a is root 3. And b is, technically it's negative 1, but it's not going to matter because you're going to square it out, right? So what do you end up with there underneath the radical once you square and add? 3 plus 1, right? So square root of 4. Or the absolute value of z then is 2. We say r equals 2. Easy enough? Okay, what's the relationship between this guy, which is b, and, I'm looking at the wrong thing. Between this guy, which is b, negative 1, and this guy, which is a, what's the relationship there? Tangent theta equals negative 1 over root 3. Okay, negative 1 over root 3. What should we do to this guy so we recognize it as a special number? Rationalize it. Multiply by root 3 over root 3. And so what does that give you? Tangent theta equals negative root 3 over 3, right? So you could take the inverse tangent of this. It'll give you let's say we're in degrees, for instance. Take the inverse tangent. It'll give you the right answer, but why? You end up taking the inverse tangent of a negative root 3 over 3. In this particular case, the theta that your calculator spits out when you take the tangent inverse of negative root 3 over 3 will be correct. But why? It won't always be correct. Which quadrant is z in? The fourth quadrant. So in which two quadrants is the tangent inverse defined? First and fourth. So when you take the tangent inverse of a negative number, yeah, it'll spit out an angle in the fourth quadrant. It'll spit out a negative angle, but that's fine. So it will spit out the right number here. But if you had the same reference angle for theta, but the actual angle theta is in a different quadrant. So for instance, if you had, you could also have the tangent of theta equals negative root 3 over 3, but what other quadrant is tangent negative in? The second quadrant, right? So it would not spit out the right angle in that case. And you'll see that. It'll come up. But just be aware of that. Don't trust your calculator. Really, you don't need your calculator for this. You should know what theta is. In terms of degrees, what would theta be? If it weren't a negative here, the tangent of what angle gets you root 3 over 3? 30. And so you can think of it as negative 30 if you like, or add 360 to it. 330, whoops. Or add any multiple of 360 and it'll work. So in trig form, remember, you get z equals r cis theta. We've got enough information to write it out. R is 2, and let's use the, you could use either angle, but let's use 330. So you get z equals what? 2 cis 330. Or if you write it out longhand, what would it be? 2 times, what does this stand for? Cis cosine 330 plus I sine 330. Whoops. You need to know how to write it both ways, because there's times when you're going to have to convert back to standard form, a plus bi form, and you're going to need to actually remember, oh yeah, I plug in 330 into the cosine here and into the sine here. Right. Z equals negative 5. Remember, the directions are to convert to trig form. Okay, you could use the formulas here, but it's easier just to draw a picture when you get z equals either a purely real number like negative 5 or a purely imaginary number like 2i or something. It's easier to draw a picture to figure out what the trig form is. So if you draw a picture here and you realize that the horizontal axis is the real axis, the imaginary axis is the vertical axis, where is negative 5 in that mess? Z equals negative 5. You just go to the left from the origin 5 units, right? It's a purely real number, so it lies on the real axis, doesn't it? Okay. So remember, we want to fill in r cis theta. Write it down, and you don't need step 1, step 2. It tells you what you need if you know the representation. That z equals r cis theta is the trig form, or it represents trig form. And what is that missing that you should fill in? R and theta, right? Okay, well, r is the distance from the origin, but it's also the absolute value. And you already know how to take the absolute value of just a real number. What's the absolute value of negative 5? 5. So we're going to fill in 5 here. And by the way, if you use square root of a squared plus b squared with b equal to 0, it still works. It's the square root of 5 squared, which is, or negative 5 squared, which is 5. But there's no reason to do that since you know the absolute value of a real number. And then what's the angle? Can you tell just by looking? So if you measure from the positive, if you measure as usual from the positive real axis instead of the positive x-axis, but you measure as usual, what's that theta? It's the straight angle, so it's 180. There's your cis form. 5 cis 180. Okay? You could do something very similar if you had like negative 5i, except you'd be graphing it down here. But it would still just be 5 units from the origin. What would the angle be if you graph something down here? 270. Yeah. Okay. Okay, the product of two complex numbers. So I had to differentiate between them, so I called the first one z1. And so it has absolute value r1 and angle theta 1. So this is the trig form representation of z1. And for another complex number, z2, this is the trig form representation of z2. So you have absolute value of z2 is r2, and the angle is theta 2. We're going to go ahead and derive what the product would be. And at first, you're going to think this is horrendous. But then you're going to see it simplifies to be a really easy-to-use formula. So let's do that. So need some room here. z1 times z2 then. If I just write it out, it would be r1 times, I'm going to use the shorthand just for this first step, cis theta 1, right? And then r2 times cis theta 2. I'm not going to do anything in that first step, so it's nice to use the shorthand in that first step. Everybody agree with that? Now, can I rearrange the multiplication? Make it r1, r2, cis theta 1 times cis theta 2. Because between the r1 and the r2 and the cis thetas, that operation is multiplication, right? So all I did was change the order of the multiplication. All right, let's write this out. Longhand. I'm going to leave r1, r2 where it's at. And then cis theta 1 in parentheses is really cosine theta 1 plus I sine theta 1. Would you agree with that statement? And then cis theta 2, same thing except with theta 2, right? Cosine theta 2 plus I sine theta 2. No disagreement yet, right? How do we multiply two quantities like this? Well, we FOIL them out, right? So let's do it. Now let's not forget to write down the r1 times r2, because these guys come along for the ride. FOIL method says you multiply the first terms together. What does that get you? Okay, let's put a big bracket here. What does that get you? Cosine theta 1 times cosine theta 2, right? Okay, let's multiply the FOIL method. First outer, inner, last. Let's multiply the outer together. What will the operation be? Plus, let's go with signs first, just because you'll recognize the identity we're about to get to a little quicker that way, maybe. So sine theta 2 times cosine theta 1. Do you believe that? For the outer multiplication? Okay. And then times I, yeah. Whoops, sorry. I was going to use a different color on that, and then I forgot to put it in all together. Times the I. Does everybody see that? Okay. And then, so what would the inner then, FOIL, first outer inner, what would the inner multiplication be? So what would the operation be? Plus, and then let's not forget the I. And then just let's put sine theta 1, cosine theta 2. Everybody see that? Finally, the last multiplication, which would be this last guy times this guy. I'll have to put it in down here because I'm going to go out of my picture if I don't. The operation will be plus at first. And then what do you get when you take the last guy? So this guy times this guy, right? First of all, you're going to get I squared, right? Everybody believe that? I squared, wait. Let me emphasize that. Everybody see that? Okay, and then what else? So we're multiplying the last guys. So sine, whoops, wrong color. Sine theta 1 times sine theta 2. And then close the, course, I meant to switch to blue right here, but I'll fix that in editing. Okay, is that okay? All right, now it looks bad, right? But there's actually some identities hidden in here, and it's going to clean up nicely. So let me group the real parts together and the imaginary parts together. So okay, I still have R1 times R2, big bracket. This guy would be a real part. There's no I attached to it, right? It would be one of the real parts. So I'm going to recopy that one. Cosine theta 1, cosine theta 2. But then this guy's also a real part, isn't it? Because what's I squared really equal to? It's really equal to -1, right? In parentheses, so you remember to multiply. So this is really a plus a -1 times all this, so that's minus, right? So minus, I'll leave that red, minus sine theta 1, sine theta 2. Does everybody believe that for the real part? And then the imaginary part, can I go ahead and factor out this I here and here? And then group those guys together. So plus I times, okay, this guy. Let me put the sine theta 1 first, if that's okay. So let me put this guy first. It's just addition, so I can reorder it any way I want. Sine theta 1, cosine theta 2, plus then this guy, right? I have to put it down here. Sine theta 2, cosine theta 1. And then close the parenthesis and then close the bracket. It still looks ugly, but do you see any identities anywhere? What would this guy equal right here? It's actually a sum identity. But which one? Cosine or sine? Cosine of, it's actually theta 1 plus theta 2. Right? And then this guy inside the parentheses here, that's another sum formula. What would it be? Sine theta 1 plus theta 2. So I'm going to replace all that with these two identities. R1, R2, cosine theta 1 plus theta 2 plus I times sine theta 1 plus theta 2. And it did clean up, but you may not realize the beauty of this formula right off the bat until you put it in cis notation. Because what is this in cis notation? R1, R2, cis, theta 1 plus theta 2. So what is this saying? It's saying that if you want to take the product of two complex numbers in trig form, you just multiply their absolute values together and take cis of the sum of their angles. It couldn't be easier, you guys. It's way easier than multiplying them out in standard form where you're foiling them out. It's way quicker, as long as they're already in trig form. Then if they're not, then it's not way quicker. All right, so let's try to use that formula. What do we get when we multiply 2 cis 30 times 3 cis 225? So that formula says multiply the absolute values together, which is the absolute values are the guys out in front. So what do we get there? So we get 6. And then take cis of the sum of the two angles. That's what the formula says. So I'll go ahead and write out that sum. So 30 plus 225. And that's what? 6 cis 2 5 5. That's it. As long as you're leaving it in trig form, right? If you weren't going to leave it in trig form, you could write it out longhand. 6 times the quantity cosine 255 plus I sine 255, and then estimate. 255 is not a special angle, so you could use your calculator to estimate those values. Here it is written out longhand, and we switch to radians, 2 pi over 5. You know what? Let's make this 2 pi over 3. It'll be a little bit more interesting that way. Okay. So what does the formula say to do with the guys outside? Just multiply them. Just multiply these guys together. So you're going to take R1 times R2. So let me remind you what the formula says. It says if you want to take the product of Z1 times Z2, you're going to take the product of the two absolute values, R1 and R2, and then add their respective angles together. Right? So that's easy enough. So back to the multiplication here then. So what does this guy become? Let me get this out of the way, just because it'll look weird if I leave it there. So we take 5 times 2 and get 10, and then it becomes cis. We're just going to add 2 pi over 5 to 2 pi over 3. So the hardest part is the arithmetic, finding the common denominator and adding those together. What is the common denominator? 15. So I could multiply 2 pi over 5 by 3 over 3. What does that get me? 6 pi over 15 maybe. And then I could multiply 2 pi over 3 by 5 over 5. What would that get me? 10 pi over 15. So we add these together, what do we get? 10 cis 16 pi over 15. Good enough. That's scratch work over on the right. Division. I'm not going to derive this formula. I'll just say that the derivation is similar. You would use trig identities. Maybe you might have to use a conjugate multiplication. But basically, if you take the same z1 and divide it by the same z2, you'll get z1 over z2 equals, okay, on top, what does that really mean in cis notation? R1 cis theta 1 divided by R2 cis theta 2. I haven't stated the result yet. This is just what it is in trig form, right? The result is this. The result is, okay, you're going to divide these numbers outside. This is just regular division, regular multiplication across, and then regular division across this division bar. So it's just R1 divided by R2. And then if you had to guess, it would be cis of, well, multiplication reduced to addition. So maybe division will reduce to subtraction. And that's what it does. So that's the formula. That's the one for division. So let's say you take the complex number 32 cis 30 degrees and divide by 4 cis 150. What will that give you? Well, you know how to take 4 into 32. What's that? Start with that. 8. And then cis of what? According to this formula, what are we going to do? We're going to take 30 minus 150. Take cis of 30 minus 150. And so what does that get us? 8 cis negative 120. What's an equivalent representation if you wanted to write this using an angle between 0 and 360? So this is an or. I mean, this answer is perfectly good. Or 8 cis. Well, this is an angle that when you take the cosine of it and the sine of it, if you just add 2 pi, you'll get, or in this case 360, you'll get the same answer, right? The period of cosine and sine are, the period's the same, and it is 360. If you add 360 to negative 120, don't you get positive 240? And if you take the cosine and sine of 240, you get the same numbers. So careful what we're saying here. Negative 120 and 240 are certainly different angles, but they have the same terminal sides. So when you take the cosine and sine of them, you get the same answer. So either answer works. Does that make sense? So to go from, say, negative 120 to 240, I added 360 degrees. That's all I did. Okay. Now, be aware, in the homework, you'll be given some problems like this, but you'll also be given numbers in standard form. So you'll have to convert to trig form first in several problems in the homework. So be aware of that.